my talk, is of a different flavor, this time. I like to break the protocol, the reason I do that because, this talk usually is posted on YouTube, and many of my students says, "Can you please talk some English with something we understand? Can you make it general so we can understand?" Your talks are too too focused, and so on. So that's one reason I'm going to make it very general talk, okay, to be accessible to students who watch the video and so on. But at the same time, I'm trying to balance it so that it won't be boring for you too. Okay, the talk is intended to show you my experience working with undergraduate and graduate students on master's thesis, and on senior project at the undergraduate level. Okay, I will show you what problems I did with them, what problems we would like to work on, and basically the thing I would represent, it's accessible to students and with different levels of difficulty. So some kind of research is appropriate for undergraduate, some for masters, some for PhD students. So different level of difficulty. Okay, so here is the title of the talk: Fixed point theory and Green's function for the solution of differential equations and iterative strategy. It's basically iterative methods in numerical analysis. Okay, from my experience for the past years, working with students in my formal institution, which is American University of Sharjah, which is in the suburbs of Dubai. Every year, if you have two tracks, pure mathematics and applied mathematics, less students are interested in pure mathematics. They would prefer pure applied mathematics. Talking with students say, well, we need to find a job, applied mathematics, you can work with softwares like MATLAB, Maple, and companies love these. They don't care if you teach calculus or differential, they care about the software you use during your study. So that's one reason. Another reason, one of the students told me, the problem with theoretical mathematics, you have to focus. And how can I focus? And every 5 minutes I get a WhatsApp message or so on. So you have to keep focused, all the time. So there is lots of distractions, which is the reality these days. Okay. Now, also another thing from my experience, always, we try try to solve the situation in the math department. Less students interested in pure mathematics, so sometimes we come up with this major in mathematical biology, or sometimes actuarial science. It comes for a while, then it dies down. Then economics, mathematical economics, actuarial, and nowadays everybody wants to do data science. So every 4 years, but whatever you do, you end up to the theoretical part. In any case, so this is kind of numerical methods, fixed point, iterative methods in numerical analysis. Okay, so I will state the problem. I will introduce the method that I worked with my students on. We created this method, So just very quick overview for Green's function. I hope you all know this one, but it won't be boring for you. Overview of fixed point iterative procedures and method description. We have I'll show you some convergence analysis and some numerical results. Okay, so the problem is here. You have a differential equation. Okay, L is linear term, N is the nonlinear operator, and F is a function. This is linear operator, nonlinear. So if we take an example of this, let's say this fractional boundary value problem, very simple one, with boundary conditions, alpha between 1 and 2. Okay, we need to find a numerical method to solve this fractional boundary value problem. So that's the idea. Okay, now, overview of Green's function. Let's take this nth order linear differential equation where the non-homogeneous term is f of t. The idea of Green's function, if you replace f of t by the delta direct function, and if you can solve this equation where f is replaced by the delta direct function, then you can solve this problem. It's very known. Why it's easier for the delta function here to be solved? Because delta is roughly 0 everywhere, except at one point it blows up. So, by the way, the Green's function is the solution for this differential equation where f of t is replaced by the delta direct function. Okay, so of course this differential equation should be complemented with boundary condition so that it will have exist a solution and so on. Okay, so this is my operator L. So I want to solve it where f of t is replaced by the delta direct function, this one. Okay, so the solution is called the Green's function. Okay, so going back, the Green's function for t bigger than s, it is delta direct function, it is 0, less than s is also 0. All right? So if it is equal to 0, solving nth order is basically n linearly independent solutions, for less than s, and if t bigger than s, another n linearly independent solution. This is the solution, the solution of linear differential equation. Now, how do you get these coefficients? You have how many coefficients? 2n coefficients, right? 2n to determine the Green's function. Of course, we have n boundary conditions. Okay, n boundary conditions. So G satisfies. Okay, but always we want the Green's function to satisfy the corresponding homogeneous boundary condition. So if you have u of 0 is 2, the Green's function should satisfy u of 0 as 0. So we have n what? Boundary conditions. So we have n constants left. So basically the Green's function, since it is nth differentiable, so the Green's function should be continuous. First derivative continuous, second derivative n minus 2 continuous. So this is the second condition. Now let's look at the third one. So this results in a system of equations. Okay, but we have how many left here? We have n conditions and n minus 1, so we have less one condition. Now look at this one. If you go back here, so the n minus 2, its derivative is the delta function. The n minus 2 derivative, its derivative is the delta function. Mean the nth minus 2 derivative is the unit step function. Because in the generalized sense, the derivative of the unit step function is the delta function, right? 0, 0, and it blows up. So this is how you determine the coefficient. So the third condition will be, you see, we have the jump. Okay, it's an of s is the coefficient of the highest derivative. If the highest derivative is coefficient is 1, so we get a jump of 1. So you got the last condition. It is based on the idea that the derivative of the unit step function is basically the delta function. So we have a jump. So this will determine the Green's function. Okay, now you know the Caputo fractional derivative definition here. So this is the Laplace transform for fractional derivative. We have this term extra. Okay, so now let's take one example just quickly to introduce the Green's function. So let's take this boundary value problem, alpha between 1 and 2. So we need to find the Green's function. So f is replaced by the delta function. G satisfies, notice, the 0, the corresponding homogeneous boundary conditions. Okay, to find the Green's. Okay, this is the Green's function here. Okay, as a piecewise function, this is how it looks like. By the way, the Green's function is not only, I'm mentioning it to show you the numerical method using the Green's function, but usually the Green's functions are used to show existence of solutions, also for boundary value problems. Another problem, if you have y alpha minus lambda squared y, this boundary condition, so the Green's function for this case, also you can apply Laplace transform. Here is the Green's function for this case. It's looks very complicated. And EAB is the Mittag-Leffler function. This is, maybe I went so quickly on the boundary value problem. Just I added this term, minus lambda yt, so the Green's function looks very complicated now. The funny thing, one of my students did it for alpha equals 2, and the Mittag-Leffler function reduced to the sine hyperbolic function. Okay, here is another example. Oh, this is now initial value problem. I intentionally put an initial value problem. Okay, because if you do the Laplace transform to get the Green's function, here is the Green's function. It's one piece, not two pieces, 0 from the other side. So please keep this one in mind. So this is just a quick overview of Green's function. Okay, now let's go to fixed point theory. How to find the fixed point. There is lots of literature on this one. We were not that interested in deep, theory of this one. But to find the fixed point, we have this famous Picards. We have Krasnovsky's iteration. We have this parameter here. By the way, if alpha is 1, if gamma is 1, then this is reduced to Picard. Of course, this Krasnovsky iteration was generalized by man. So it's not one constant here, it's a sequence of constants. The sequence is between 0 and 1. And we have Ishikawa, it's kind of implicit iteration. This is to find the fixed point. Fixed point, important because you can think about the fixed point as the existence of a solution for a differential equation. If you show that there is a fixed point, then in a way it means you have a solution for the boundary or differential equation or initial value problem. Okay, now method description, okay? So the method here, the numerical method is based on a combination of fixed point iteration method with Green's function, with operators, Okay, so we have this, let's say, this fractional boundary value problem, very simple one. Oh, by the way, I mentioned before that if you solve the problem where the non-homogeneous term is the delta function, then you can solve it with f, So a particular solution is this one, Okay, so if you solve it, if you find the Green's function, then with the non-homogeneous term is f, so this is the particular solution. I forgot to mention this. By the way, this is true particular solution for the problem I mentioned earlier if the boundary conditions are homogeneous. But in general, there are more terms like for example, the previous one that I showed, this one, the particular solution will have some terms outside. From now on, so it's not exactly the particular solution is the integration of g times f. So there is some terms outside depending on the boundary conditions or the initial conditions. Okay, this term I will not make it appear later on because when I do the iterative scheme, I'm going to assume this one to be the initial iteration, Okay, so the latter term outside the integral will not be visible in the iterative scheme as it is set to the value of the first iteration. So the first iteration will be this one. Okay, so here is the method. Define this integral operator. Okay, y alpha here. Okay, subtract f, add f in a way. Notice that if y is replaced by yp, then this term will be the particular solution. Okay, but I erased these terms outside. There are some other terms outside the integral, Okay, so we get this one. Now for this operator here, you can apply any iterative scheme you want, fixed point iterative scheme, and you come with a numerical method. So here, if you apply Picard, so you get this iterative scheme. Of course, for my students, they have to do integration. Sometimes the integration is not possible, but there are many numerical integration methods, Simpson's rule, trapezoidal rules, and so on. So they have to handle this one. So this is Picard. Amazingly, man's iteration this one mans, where beta n is a sequence. It's the same as Picard, look at it, the same, but you have this sequence coming out outside the integral. You see? Only this one. By the way, if beta n is 1, it reduces to Picard's iteration. Now, the lack of theory in this thing, this is easy to, implement it on a computer algebra system like Maple or MATLAB, and use some numerical integration to generate the iterates, for example. Okay, the problem is this: the beta n. What is the optimal value for beta n? This is the lack of theory. I'm telling you, we're looking at this. How do you know that man is better than Picard? Sometimes if you apply for certain boundary value problems, you'll find out beta n to be 1, which is Picard. But how can you know theoretically that Picard is the best one? Or how can you know that man is the best one? And if you know, how do you determine the optimal value of beta n? Optimal means which one value of beta n which gives you the fastest rate of convergence. Okay, for the students, they do trial and error. They tell me, oh, this is the best beta n. Okay, another problem numerically speaking, from a numerical point of view, it's not convenient that at each step you have a beta 1, beta 2, beta 3. So we'd like to have a balance, between them. But sometimes it is not possible. At each step, you have to have beta 1, beta 2 for the method to converge. Okay, so there is lack of theory on this for a certain class of differential equation or boundary. How can we determine the best beta n, the optimal one? So this is kind of research we're working on. Okay. All right, one of my students suggested since we don't have enough theory behind this one, how to choose the best beta n, she tried to minimize the L2 norm of the residual error. Residual error, if you have y double prime equals f, so, when you have approximate solution, you don't get y double prime equals f, roughly f, So the residual error is when you substitute in the equation and you get roughly then an homogeneous term. So it's the difference, So she tried to minimize the L2 norm of the residual error to obtain beta 1, Okay, that was very successful, and it matched with the trial and error thing. By the way, if you want to look at the man's iteration for this class of fractional boundary value problem, here it looks like this one. Okay, now we have a publication with one of our students and my colleague. We used the Ishikawa fixed point iteration. Sometimes Picard does not work, man does not work, but Ishikawa works. It's 2 steps, it's an implicit one. Okay, but the big question, how can we know? Many have the wrong interpretation about numerical methods that numerical method is you come up with a method and you prove convergence or rate of convergence. No, some numerical methods require priori theory before you proceed. So now what, shall I spend 1 year trying to figure out which is Picard, which is man better, or which is... So sometimes in numerical you need a theory in advance to know which direction you should proceed. So it's not only like, okay, I give you a method and I prove convergence. It's not like that. Some numerical methods are more complicated. So we did the Ishikawa for some class of boundary value problems. And by the way, Ishikawa has two parameters, 2 sequences, alpha n, beta n. So again, our students try to minimize the residual error. Here is by the way, the residual error. My differential equation was L of u plus N of u equals f. So L of u plus N of u minus f. You don't get 0 exactly, you get approximately. That's called the residual error. So she minimized the L2 norm in terms of alpha and beta n. So it's a surface, And it worked very nicely for this class of second order. Okay. We had, of course, this is the tough part, is how to determine the alpha n, beta n. There is no lack of theory till now. We don't have which one is the optimal values for alpha n, beta n, except we did it by minimizing the L2 norm, but this is not good enough, Okay, so of course, whenever you do iterative method, you should have to show up convergence. So if you define this operator, I'll show you one theorem, of course. And we have this theorem. Assume that the function f, which appears in the definition of the operator Tg, is that if you have this condition satisfied, then Tg is a contraction, and hence Ishikawa converges strongly to the fixed point. You can come up with many, convergence theorems. Okay, now let me give you a note from calculus of variation. Okay. Now, in calculus of variation, this is an area I have nothing to do with it. I don't do research. But in calculus of variation, they come up with iterative methods also. Okay, so the variational iteration method admits a correction function in this form. Okay, where lambda t is very popular in calculus of variation, they call it Lagrange multiplier. So in one of our papers published in Applied Mathematical Letters, it's a short paper, we showed actually in calculus of variation what the so-called Lagrange multipliers is basically the Green's function. So this is what we showed. It's basically the Green's function, so they call it Lagrange multipliers. Okay, having in this one in mind, we came up with another paper. If this is the Green's function, remember I gave you initial value problem, and the Green's function for initial value problem has one piece, the other piece is 0, right? One piece, not two pieces, the other piece is 0. So this is like from A to X in calculus of variation. Since it says the Green's function, this is appropriate for what? Initial value problem. So we said in calculus of variation, the setting should not be like this. Maybe you have something from X to B if it is boundary value problem. So this resulted in another paper, and we said, okay, listen, in calculus of variation, the setting should be here. You should have lambda 1 and lambda 2 as the Lagrange multiplier. So this came from the idea that we noticed that the Lagrange is basically the Green's function. Just a note from calculus of variation. Okay, some numerical results. Okay, take this very simple second order nonlinear differential equation with this boundary condition. We applied Ishikawa. Here is Ishikawa. Okay, it's kind of messy, So sometimes the help of students is needed, especially fresh student to go through Maple programming. It's very, very tedious work, Okay, so here is the Ishikawa for this one. This one has been published, by the way, I think in Applied Mathematics and Computation Journal, Elsevier Journal. Okay, again, how do you find the alpha n, beta n? By the way, Picard did not work for this problem. Man did not work, only Ishikawa worked. Okay, why? Okay, theoretical work is needed on this. There is very lack of theoretical work on the choice of alpha and beta n. By the way, here is man. No, I think man worked for this one. No, man, for other problem, it's not worked. So 15 terms, look, minus 10, the error. Picard, minus 9, almost the same. But Ishikawa, for 15 terms, it's like almost like the exact solution. This is for 7 terms. So 7 terms of Ishikawa, as good as 15 terms in Mans or Picard. By the way, sometimes none of them work, Ishikawa. But why does it work? We're looking at this one. Okay, so this is what my students did. So she plotted the L2 norm of the residual error. For Ishikawa, it has 2 parameters, not 1, alpha, beta, n. So you see the minimum? There is one minimum. This is the optimal value for alpha, beta. That gives you the fastest rate of convergence. And if you do it by trial and error, alpha, beta will match with this one. Okay, but, this is just, you have to back this one with theory, why this is the best one, not L2 norm. Okay, now the recent work, I'll show you now. The recent work now we're doing, or I'm planning to do, is I searched the literature extensively. We have this numerical analysis boundary layer problem. it's a very challenge to tackle boundary layer problems. Boundary layer problem is when you have, let's say, this is a boundary layer problem. It's called Trutch's problem. This problem goes 0 to 1, right? Here is 1. But for large eigenvalues, there is a layer here. So the bigger the eigenvalues, it blows up here like this. So for lambda 200, it's like this. Boundary layer problems are very challenging to tackle, numerically, very challenging. And the best, researcher in this area is a Russian mathematician, Shishkin. Okay, I'll show you some of his work now. So what we're planning to do is mimic the work of Shishkin to fractional, fractional boundary layer problem. We search the internet, there is not enough work on fractional boundary layer problem. There is on fractional, on boundary layer problem, which basically most of the work is focused on the work of Shishkin. See the problem of this one, why it's, we had a couple of papers on this. It was very challenging to solve it numerically. It's usually unstable. Okay, again, this is, if you work on numerically on boundary layer problem, you have to have a theory before you start working. What's the theory? You have to know where is the location of the layer. Sometimes it is here. It is here. If you plot this one regularly on Maple, you cannot see that there is a layer here. So where is the location of the layer? Left, middle, or in the end, right side? Another theory you need for boundary layer problem is what's the thickness of the boundary layer? This one for Trutches, in some cases for large eigenvalue, it could be 10 to the power minus 10. The thickness of the boundary layer. So you have to know the location of the boundary layer from a theoretical point of view, and the thickness of the boundary layer. Other than that, you cannot proceed. So Shishkin was able to prove the thickness and the location of the boundary layer, and he was able to come with the so-called Shishkin meshes. Meshes, Shishkin mesh is basically, you have some points here, regular mesh here, and here near the boundary layer, you increase the mesh points. But you have to come up with a function, based on this theory. So this is our current work, is working on fractional boundary layer problem. So extend the work of Shishkin if possible. So the thickness of the boundary layer will depend on the alpha derivative, for sure. Okay, why is that? It's not about our interest in fractional derivatives or calculus, but the idea is that when you do fractional differential, it gives you more layers, So in terms of modeling, you have more curves, near the boundary layer, more shapes, So when you increase the possibility of more curves at the layer, right? Then from application point of view, modeling. Let's talk. One kind of modeling of boundary layer problem is aeronautics engineering. So all the activities takes place next to the wing, right? So very close to the wing. Outside, it's normal. So maybe you can study the turbulence more. Control it more or minimize it more. So it gives you more options in terms of modeling rather than interest in fractional derivative. Okay, by the way, this is boundary layer problem. For small lambda, it's regular, but for large lambda, we have a boundary layer on the right side. This one, we could not solve it in using iterative schemes. I have to admit, they are not that, strong numerical methods, but the theory behind them, it's really interesting. What's the best alpha n, beta n, to give you the best rate of convergence, Okay, so we tried to make a change of variable. So it seems that the boundary layer looks like tangent hyperbolic. So we switch it to this differential equation. So now to get the Green's function, usually the Green's function corresponds to the linear term in the differential equation. Before it was y double prime, but now we have y double prime here, and we have a linear term here, lambda squared y. So using the Green's function idea, we transformed this one, and the Green's function for y double prime minus lambda squared y. Well, I showed you this one before, the Green's function for y double prime minus lambda y. So we use this, actually Picard works fine. And after this transformation, only the iterative method works, but without this transformation, it will not work. Actually, for this is for different eigenvalues. You see this is the numerical solution. Here it is like here near the boundary, it is almost zero. The larger the eigenvalue, you get closer. It is zero here, very close to 1, you see? So we get for all eigenvalues. Amazingly, the iterative method, the bigger the eigenvalue, the fastest it converges. We were lucky about this one. Of course, numerical work, you have to compare it, otherwise it's not publishable, So we publish this one. And this is the Trotsky's problem. You see the boundary layer for different eigenvalues, this is 30, Okay, so recovering the boundary layer is not, this is for 100, Okay, but the iterative method failed if we, if we did not do transformation. Okay, so our work now is focused on fractional boundary layer problem. It's going to be very challenging, theoretically. And we're looking at the papers by Shishkin, grid approximation. This is second doctoral thesis. I don't know what's second, whether there is first or second. Probably you know better than me. And so we're working on Shishkin work to extend it to fractional boundary layer. I think I stop here. Thank you so much.